So I'm Chris Kempis, resident faculty at the Santa Fe Institute. I'd say one of my main interests is life as a phenomena. So I think the way that we've typically looked at or thought about life is in its diversity. So we've been very interested in individual species and how a particular species fills an individual niche, what its evolutionary history looks like, why it has the particular form that it has. And I think all of that has a lot of aesthetic beauty and is a very interesting set of questions, but I think the next generation of biology really needs to find ways to systematize a theory of life across all of that diversity and to think about life in terms of a set of general principles and in terms of sort of one universal theory for life. And I think that such a theory has both a lot of application to very basic science questions, like how did life start and where else it might exist in the universe. And then at the other end, such a theory also has a lot of application to things like bioengineering and ecological management. And so I think this is exciting. And so what does such a theory look like? I think we can answer that from the perspective of what it should do. And so a general theory of life should be able to explain how life started, how it evolved, how it stabilized its own environment and allowed for its further persistence, how eventually it became more complex, and then what happens when that turns into a global ecology. And so embedded in those questions are all the things on the basic science side that I mentioned, origins of life, the history and evolution of life. Both of those are also related to things like astrobiology. And then those later questions in terms of ecology help us understand sort of the current global dynamics that Dan mentioned that we're currently facing. So there are, I think, two different ways to sort of approach uncovering more of this, or more of a general theory for life. One end is to try and take the principles that we already know and put those, sort of further abstract those. So we know about things, so we have very general theories for things like inheritance, what's required of inheritance in order for life to be able to both maintain its existing memory of an environment, but also evolve into the future. And so we can start to abstract those sorts of principles to then be able to look for, say, generic biosignatures in astrobiological sense. So that's one area where we can use theory to really abstract the types of things we already know about life, and then take the specific observations we have and put those, use those as one subset of a much broader perspective on what we might expect to see. And then the other end is that we have actually lots of existing theories for ecological dynamics and processes. There's lots of arguments in ecology about what's the right theory of the process of species competition, for example. And in that case, I think what we can do is use the existing theory to then make predictions about the types of data that need to be measured to distinguish between different mechanisms and processes. And so on that end of the spectrum, I think there's a huge opportunity for us as a community to start putting together data sets that cut more across time and space at much bigger scales, so much higher resolution temporal dynamics of, say, species abundance in an environment over much longer periods of time, and then also to look at this at broader spatial scales to understand which theory of ecology we really believe, and use that to allow us to make predictions into the future about what's happening to ecosystems and what we should expect. So I think I'll keep it there for now, but I think there's a pretty broad potential here for thinking about what life looks like into the future and being able to find a structure that allows us to predict life at all of these different scales of time and space. And I can get a little bit into the bioengineering later. But thanks.
Hi, I'm Jennifer Dunn, and I am a professor at SFI, a resident professor, and also vice president for science. And I'm going to follow on both of elements of sort of the problems we face, climate and other things, and also what ecology offers in the broadest sense. So I'll talk a little bit about what I see as both the past and the future of coupled natural human systems research, also gets called socio-ecological research or socio-ecological environmental research or many things. And before going forward or thinking about the 80 to 100 years in the future, I want to look back briefly. Ecology was actually only coined as a term in about 150 years ago by Ernst Haeckel in 1866, 7 years after The Origin of Species came out. And ecology was actually, he coined it to mean the economy of nature for those economists or economically inclined people in the room. There's a very tight, relationship between economy and ecology. They're kind of an adjunct a few years later. Human ecology, something called human ecology, was finding its roots in geography and sociology departments in the late 1800s. And the term human ecology first appeared in a book written by a woman in 1907 called Sanitation in Daily Life. Actually a very important topic. And it was defined as the study of the surroundings of human beings and the effects they produce on the lives of men, I would add, of course, women. And it recognized humans as a part of and rather than separate from nature. And the term made its first formal appearance in the field of sociology in a 1921 book, Introduction to the Science of Sociology. So those are just a little bit of historical notes, looking back 100 years or more to some of the roots of this stuff. By 80 years ago, this was considered a very fragmented field. A 1944 review in Social Forces called Ecology and Human Ecology, the author stated, "Perhaps it is to be expected that the sudden ascent to popularity of an innovation in scientific thought should be accompanied by a certain amount of confusion as to its specific connotation. If so, human ecology has satisfied expectations, for after 20 years it remains a somewhat crude and ambiguous conception. A perusal of the literature that is accumulated under the name can hardly fail to produce bewilderment." And went on to say, however, very few persons who regard themselves as human ecologists indicate an awareness that they are logically committed to follow out in the study of man the implications of ecology. And, now coming up 80 years to the present, this kind of research, I think, continues to be quite fragmented today. And, that's both kind of a limitation, but also an opportunity. I mean, given that, as you all know, and as Dan alluded to, we face a variety of major challenges on this planet, climate, extinctions and invasions, socio-political challenges, epidemiological challenges. You'll hear more about that later. And while these kinds of challenges are very scary in many ways, and the increasing rates and magnitudes of change we face, they also provide a really unique set of opportunities over the next 80 to 100 years for transforming our understanding and the science of coupled natural human systems, and also their application at different scales to these major challenges in terms of understanding, forecasting, and prediction, innovation, and response of various kinds, mitigation and adaptation, which Dan alluded to. What do I see as a successful research trajectory over the next 80 or 100 years? And my own work is starting to get out into this realm. I see a successful research trajectory being one where ecological, environmental, geological, socioeconomic, political systems are always studied in conjunction with each other. And it is a given, rather than exception, that they are studied in a deeply integrated way. And that's still very much the exception rather than the rule, although it seems fairly obvious, I think, probably to everybody. I think we will have the opportunity and need to develop multi-scale, empirically supported theories of non-equilibrium dynamics in coupled natural human systems that consider a wide variety of mechanisms, statistical, thermodynamic, evolutionary or historic, ecological, geological, and behavioral psychological. I think as with all studies of complex systems, where we're moving is into developing theories that have explicit an explicit basis in the currencies of both energy and resources on the one hand and information on the other hand. And we'll hear more about this explicitly in other people's talks. I also think it requires us to have a much clearer understanding of the limits to and appropriate levels of prediction or forecasting. Prediction of fine-grained dynamics is unlikely, but there's many, many opportunities to forecast or predict more coarse-grained variables and dynamics. And I also think, kind of hand in hand with that, a successful trajectory will transform how we educate the public and policymakers about the role of uncertainty in scientific understanding and other kinds of these and other kinds of complex systems. I think that's critically important. Just in terms of what I think is limiting progress on these things, I think there's intellectual limits. There's currently a strong tendency to fall in what I called yesterday strong suboptimal local intellectual minima, driven in part by disciplinary siloing, by bandwagon phenomena due to a lack of imagination and often a fear of professional non-advancement, and also by the strong influence that a few leaders often exert. Like in ecology, over the last 50 years, there's been an overdominance of small-scale experiments and competition-based theory and explanations. In socioecology, there have been various kind of dominant but kind of fairly narrowly defined areas. The Elinor Ostrom's collective action approach to sustainability of small-scale natural resource pools, very important work, but again, people kind of bandwagoned on the one hand, and then also you've got things like the Jared Diamond style collapse narratives, so you tend to get a lot of attention on those things, but there's a much broader kind of landscape of work that needs to happen. We have institutional limitations, outdated institutions and processes, discipline-based evaluation and reward systems for funding publication and career advancement. There's a lack of theory, and as a result, a limited ability to generalize and ability to grapple systematically and comprehensively with multi-scale phenomena. This is really especially true in the social sciences. I think Chris highlighted briefly that ecology is, I think, moving very strongly in the direction of quantitative theory at different scales about life, which is great and needs to continue. There's also the limitation of what I call the handmaiden effect or the veneer effect, where social science is just like a veneer put on ecological studies or vice versa. And data is still very heterogeneous in quality and quantity. We have a ton of data on the environment side. On the ecological and social science side, it's much more heterogeneous and variable and also highly biased as to what kinds of data we have access to for what kinds of systems. But at the same time, we can't just assemble ever more case studies. We need systematic, thoughtful comparison, synthesis, and integration. And data compilation needs to be driven by questions in quantitative theory development and testing. And that's pretty much what I'm going to say. There are new institutions arising, including SFI, of course, that are where people are grappling with these kinds of things. You also have places like the Stockholm Resilience Center, the Socio-Environmental Synthesis Center funded by NSF. There's now an international long-term ecological research study sites, which a number of which are explicitly including an S into the ILTER. So the social, too often still that's kind of the veneer of social research on top of ecology, but I think we do need to keep diversifying in terms of our institution and opportunities, and I'll leave it there.
Nigel, do you want to start us off with a few questions for the panelists?
Yes, great. I think we could have all day just on those three inputs. But I've got a couple of questions. I want to start with Dan, but it's picking up on this point, Jennifer, about the kind of desire for predictability in models, but also the need to understand uncertainty. One of my favourite phrases in the conversation yesterday was the distinction between artificial intelligence and real stupidity, which seemed to come up over and over again. And Dan, you talked about the kind of tyranny of a certain type of model, kind of general systems models, and I think I wrote it down. You said it's extraordinary that anyone takes them seriously, and yet you've worked in policy, and there's a certain type of model which gives the impression of very accurate prediction doesn't shed light on uncertainty, particularly the kind of complex interactions between markets, policies, and the social response we talked about. Can you just say something about how a complexity approach might be more helpful to business leaders and to policymakers in navigating that difference between the need for some predictability and the need to understand uncertainty?
Yeah, I think we struggle with this all the time, and actually, what Jen was saying, I think, is true every day for a climate scientist who deals with models a lot. But we also have a pretty deep understanding of the limitations of our models, and what they can say and what they can't say. And I think the public, I would say in general, the public's understanding of limitations on this kind of modeling has improved dramatically over the last 20 years. I think it's intuitive for everybody what the limits to prediction of weather forecasting are, because of experience. Because they experience it so regularly, they know not to believe everything in particular, but they also understand that, forecast today on a Wednesday of what Memorial Day weekend is going to be like, is reliable, although things might shift a little bit. They know when there's a forecast for a really big storm, maybe it'll fizzle out, but it's certainly something that you might prepare for. What's interesting with climate change is we also see this climate forecasts. 30 years ago, climate models were capable of maybe telling you global average temperature a little bit. But regional stuff was probably not reliable. Today, they've improved. Sorry, you want me to get closer? Sorry. I've also been like, this is a little bit like singing in the rain, where I keep going like this and then that, making it hard for the camera. So I'll speak into the microphone. I think today climate models are much, much better. And so the answer is you can believe regional forecasts. I think, a 50-year forecast of what the average, meaning average over 20-year climate for New England, I think has some reliability. That doesn't mean there aren't uncertainties, but I think there is some predictive skill. Unfortunately, we've seen that abused. I was involved as an external advisor to the city of Cambridge. They were doing a climate impacts assessment for planning purposes for how they should prepare for climate change. Cambridge is one of the more progressive cities in the US, and so that not surprising they were out in front of this. And they hired a consulting firm who hired some researchers from the University of New Hampshire and provided them with a downscaled climate model that predicted street by street, literally neighborhood by neighborhood in Cambridge, a map of what the precipitation and temperature would be seasonally in Cambridge. So the difference between Harvard Square and Porter Square. Needless to say, I was horrified. And what the consulting firm, and this was, they'd hired some PhDs. Actually, I think they were from MIT. So, but they hired some recent PhDs from MIT who were now working for this consulting firm, and their response was, look, city policymakers, the mayor's office, they need to have something on which to make a decision. They can't just make a decision by you telling me it's going to be warmer. They need to see a map. And I said, but your map has no value, and that didn't perturb them at all. They wanted to give the policymakers something to make a decision. That is a horrifying future. And so I think one of the things that's really important as we talk about this are, what are the elements that actually have predictive skill? What are the things that we can understand, and what are the things we can't understand? And as Jen said, there are some aspects that will never be forecastable. I also think we need to distinguish between patterns and theory, mechanistic theory. I think that sometimes is lost on people. a lot of the scaling work, for example, that Jeffrey's doing, I see Jeffrey nodding over here, a lot of the scaling work is pattern, is real pattern. There isn't necessarily theory underneath it. I think what Jeffrey is doing is trying to backfill with theory, and that's why it's important. But there's a lot of pattern out there. One of the challenges in a situation like climate change is that the past is no longer necessarily a predictor of the future, and so the patterns that we're used to may or may not be valuable. Unless you have a theory. And that's why that's exactly the point. And so I actually think a lot of what SFI is about is putting theory behind patterns that we see in the world. And I would just put in a pitch here, and this goes way beyond climate. It goes to everything we're talking about: biology, social systems, physical systems, everything that SFI works on. To me, there is a rush in this new world of massive data, computer technology, machine learning algorithms to treat everything as a search for patterns without mechanistic understanding. And to me, I hope that SFI will continue to be the place where we think deeply about theory underlying things. And that is fundamental to what I think the mission of SFI is. But maybe I'm overstepping my role there. But I think it's really, really important in this day and age when there's so much promised purely by data and pattern recognition.
Great. Thanks, Dan. Chris, I wanted to pick up on your idea of I love the idea of a grand systematic theory of life that we have in 80 years, which to Jen's point, could be applied at multiple levels. So the cell, the organism, the ecology, the planetary society, and the socio-economic systems. And you talked about understanding how life starts, how it evolves complexity, stabilizes, and creates an ecology. And it seems to me that some of these big questions we're having now about how does one maintain a healthy ecology or a healthy system, could you say something about how looking at planetary biological systems and in silico biological systems might shed light on what Johan Rockström, who's at the Stockholm Resilience Centre that Jen mentioned, talks about what is a safe operating space for humanity, and how might we learn from this kind of work on life systems in a way that might be applicable at different orders of magnitude, at different scales?
Great. So I think part of that Dan could actually talk a lot about, which is if you look at the past, right, then understanding the systematic patterns of the past help you to see how quickly radical change can happen, what's likely to cause extinctions, how much of an impact life can have on the entire planet. I think at the the current ecological end, knowing things about detailed physiology and evolutionary processes tells you something about how the types of changes you're expected to see, right? And so knowing that dispersal and species competition happens much more quickly than evolution tells you that some shift in the environment is more likely to lead to a redistribution of the types of species that are there rather than a quick evolution of species in certain environments. And now that shifts a lot going from microbial life to multicellular life. So knowing something about these different growth rates, these different sizes, what it means to be a bacterium or a photosynthetic organism in the ocean compared to a large vascular plant, there are really different processes happening there. So at the small end, the types of ecology actually can undergo evolutionary processes to adapt to an environment. Adaptation to a different temperature, for example, is a fairly quick evolutionary process. That's much slower for vascular plants. And so vascular plants, you then have to count on the redistribution of species to adapt to a shifted environment or a changed scenario. And so, to Dan's point about, different types of models, that also informs how you model the biogeochemistry of the ocean compared to the terrestrial biosphere, because there are different types of processes that you have to include in each of those models. So that's one place where just a very basic understanding of certain biological processes has big implications for how you model different systems and the types of processes you need to consider. And then in terms of, the sort of more, kind of basic bioengineering that happens, I think the sort of growing understanding of systems biologies and how genes fit together, that just opens up a variety of possibilities for the types of organisms you could design to do specific features. With that comes an entire set of consequences, ethical dilemmas, things to consider, because as you engineer a species for one thing, you don't always know the sort of side consequences it might have. So there are people who talk about, for example, using bioengineering as one way to do geoengineering. So how do you redesign organisms to put in ecosystems to do certain types of features as one path to geoengineering. But to do that, you have to understand the broader ecological consequences, the long-term dynamics, and that becomes a hard problem. So I think that's the place where both action and modeling require these different scales of very detailed biological knowledge.
Can I just jump in really quick
Yeah,
there?
please.
Because I think that's a really important point. I also think it's important to remember that we live in a small time scale of Earth history relative to the time scale over which evolution has operated. So, for example, as you say, some people propose that we can bioengineer trees to take up carbon faster, grow faster, and take up carbon and essentially solve our problem with climate change. I've always been very skeptical of that for the simple reason that we're very good at engineering biological systems to do things that nature's never selected for. We can make cubic tomatoes to pack them better. That's because nature never had a reason to make cubic tomatoes. It's, that's honestly, we can do that. But making plants grow faster, turns out organisms are complex systems, and nature has selected for that heavily, heavily, heavily. So, if plants could grow faster, they could outcompete their neighbors in all sorts of ways. That would be a highly desirable trait. But there are trade-offs in terms of nutrients, in terms of all sorts of other aspects. And so, it turns out that land plants have been around for about 350 million years. And that's a lot of generations in terms of selection. And I tend to think that, if there was a way to make plants grow faster in the context of all the other complex trade-offs that are around, nature would have figured out how to do it. And that I think it's unlikely we're going to actually figure out the perfect way to do that. Now, there's some people who disagree with that, but I would bet on evolution on that particular aspect. That being said, there's some interesting other ideas out there. Some people have said, when people were excited about cellulosic ethanol, they said, let's engineer plants that have more cellulose and less lignin. Forgetting that plants are not just sugar producers. They actually have other functions, like they actually have to stand up straight and grow. And so if you take away the lignin, and guess what? Plants can't stand up. That's not a very good design. So it turns out, I think we will gradually become more sophisticated in our bioengineering, but there's some things that I would say evolution is highly selected for already, and I would say we're unlikely to outcompete just because of the time scale over which natural selection has operated. But Jen is about to jump in.
Yeah, and I mean, in addition to the very important evolutionary argument that Dan just made, there's also the ecological context. I mean, it's not just modifying a plant in a certain way to achieve some goal. They're embedded within a network of interactions with other species and with the environment and with humans. And you throw...
Well, we've already dashed that to hell, so...
Yeah, but again, we've dashed that to hell, but every time, if you introduce something, you may think you know what it's going to do, as you pointed out, but it's going to alter, its interactions with microbes, which are going to affect, soil carbon. And, there's so many ecological knock-on effects that, and it's not that we can't necessarily try to understand those better. We can. I think we often don't. Humans tend to be fairly short-sighted in these kinds of things. So, that's another place where kind of a complex systems approach and certain kinds of tools like network theory and analysis can be very helpful for trying to be very careful in thinking through the potential impacts.
Yeah, just go on. And I've got a follow-up question for Jen, then we'll wrap.
Yeah, I just want to say something really quickly about Dan's point about trade-offs, which is, I think that's completely right. And the biological focus thus far has been very much on traits. And so the question is, how do you get at trade-offs? And I think to get at trade-offs, you need a common currency. And all the things you described, I think, have this common currency of physical constraints. And so I see that as a big part of the types of kind of biological theories we need to build for the future, is systematizing the physical constraints into biology so that you can understand what all the correlated knobs are for the traits of organisms. Yeah.
And does that extend then at the planetary level to this idea of planetary boundaries being the physical constraints for the planetary system?
Yes, and then
including
that would
including
be
socioeconomic.
Yeah, that would be a natural piece of that, because
Yeah.
you understand how temperature and gravitation, all these things matter for species at different scales.
Great. Well, that kind of links to what I wanted to just finish with a question to Jen about thinking in an integrated way about socioeconomic and climate and ecological and extinction things, and something which you kind of alluded to a little bit, Dan, in terms of this your comment about nudging versus shoving, and it popped up in the conversation a bit yesterday. So I think it'd be nice to bring out what does complexity approach have to teach us about how to get to and how to use kind of normative systems goals, how to because in terms of policymakers and businesses that matters a lot, all right? And is it doable? What's you mentioned the ethical. There's an ethical dimension to that, but it seems that if we're silent on that, then we miss the fact that those goals do exist within the system politically as much as anything.
Dan.
I mean, welcome to science, right?
Yeah.
I mean,
I'll let Dan
from the
take this
Manhattan
one.
Project to everything that you can think of, genomics. I mean, guess what? There's use and abuse of just about every scientific great discovery that we know about.
So my question: how can we bring out the importance and the role of those normative goals, because they exist anyway? If we pretend they don't
They
exist,
absolutely exist, and I think here in the Center for the Environment, we have a program on solar geoengineering that's highly controversial. We think of it as a positive thing, but it can also be weaponized and used badly. That's true for the human genome and all of the knowledge and CRISPR. That's true of just about every time you understand something deeply, there's a potential for misuse of it. To me, what's nice about SFI as an institution is that there's always been a commitment to including philosophy, including the conversation about the use of those technologies. But honestly, to me, that's a broader societal discussion. I still think the core mission of scientists is to push our knowledge forward, and it is then a broad conversation in society to understand and think about how knowledge is used. But I don't think it's exclusively on the scientists.
No, I wasn't suggesting that. My question was really about how can you include those normative goals in complexity models so they're not just exogenous, they're actually built into because they also evolve, right, as society reacts.
I gotta say, that's a very interesting question.
That's a
Nigel.
very hard question.
That's a hard question.
I'm
think it's
pleased
particularly
to end on a hard question.
Well, I have a colleague named Andy Hoffman at the University of Michigan, who's actually in the business school there, but he's written something very eloquent about climate change and slavery as an analogy. The analogy is that he would argue that in the 18th century, whether in England or in the U.S., there certainly were some abolitionists who thought that slavery was a moral issue, but most people didn't. Most people saw slavery as an economic issue, as kind of a way of the world, and they didn't, and they recognized the underpinnings, that the economy depended on it, and they didn't think of it as a moral issue. That was true in the U.S., really. Many people didn't think it even up until the Civil War. And even through the Civil War, there was a debate about the morality of it. Think of it this way. John Brown was some left-wing freak radical, right, who raided a federal arms depot. And a few years later, the soldiers were singing his name, marching into battle. That's a pretty big moral shift. What Andy Hoffman argued is that the morality of climate change currently is not dominant. There are some people certainly who see it as a moral issue, and I think the children going on strike is a
Yeah.
certain push that direction. But I would say for the last 20 years, most of us have seen climate change as an economic, technology,
Yeah.
environment issue, not a moral issue. Andy would argue that in order for the changes to take place, morality has to shift. But to me, what that raises is a very interesting question, which is how does morality, technology, and economics interact?
Right.
And that's a very interesting question. For example, 500 years ago, if you had said child labor is immoral, people would have looked at you like you were insane.
Yeah.
What? We work on farms. Of course children work. That's not a question, right? It was the Industrial Revolution and and technology and economics that led to our change in morality. And so I think the idea of morality being absolute, it's a very complex issue, but the question of how morality, technology, and economics and sociology evolve together, I think talk about a complex system. That's
Yeah,
really
that's the
interesting.
ultimate. And I think, there are people who are kind of, the ways in which this is manifesting that I'm most familiar with are things that go, they're well beyond the science. And it's things like the Natural Capital Project out of Stanford and University of Washington and Nature Conservancy and many other players who are, bringing scientists together to work with governments at different scales, and also to work with stakeholders at different scales, and trying to do it in the context of research around ecosystem function and what that brings, and how we need to move forward. And, it's everything from bringing, local decision makers as well as, local stakeholders like fishermen, if you're looking at a fisheries, and bringing the scientists together and trying to hash out, issues both around what the best science is that can be thought about, and bring that together with the normative and the preference issues, of the stakeholders, and then what can be done on the policy side and what can't be done. And you're getting, well beyond, kind of the fundamental science. I mean, scientists, we're trying to bring the best science we can to the table, but, what's done with that, kind of like Dan was saying, that's a decision that involves a lot of different kinds of people at the table.
And by the way, there's a real danger here. I think there are some fields of science that have gotten contaminated with teleology,
Yes.
that including conservation biology, where, again, I'm an environmental scientist. I happen to also care about the environment, but I'm not I separate my environmentalism from my environmental science. And I think that's very important. In a field like conservation biology, those two are intertwined in a really uncomfortable way. And frankly, a lot of that science feels sometimes like cherry-picking examples to justify your political position, which is really bad science.
Yes,
And
absolutely.
I think this raises a red flag saying, you know what, when you're talking about these kind of issues, and climate is certainly an area, you have to be very careful about, it's not that you can't think about these issues or even be involved in these issues that are more outside of science, but you have to be very careful not to let it affect your scientific judgment and your scientific critical analysis.
Yeah, and I also want to come back to this point we've all touched on about what good theories do for you. And I think in these cases, these are very hard problems. But if you have two really good theories, it makes putting them together much easier. And so I think a nice example of that is sun physics. So heliophysics is an incredibly hard problem that lots of people are working on. But it would be much harder if we didn't have theories for magnetism, plasma physics, thermodynamics, gravitation. But because we have all those sort of more complete theories, you can couple them together in this hard system. And so I think the goal here is both to make macroscopic models that do all these things, but also within these subdisciplines that are still hard and unsolved, create better theories there that then can be combined.
And so maybe with that, what I'd like to do is open it up to the entire room to have some interactive Q&A with the panel. Walter?
I'd like to get back to a question, comment David raised, and was included in everything you said. Sort of this long feedback cycle. And I wonder, maybe Dan, you might know, isn't there a way of finding more shorter term or mid-term signals that correlate with long-term outcomes, so that you know, like I imagine in the fight with disease, and if you have a systemic disease and it's very difficult to cure, it's a long-term process, but you may have short-term indicators whether you're on the right track based, of course, on some theory or understanding of the disease. And based on those short-term indicators, you can then modulate your strategy. So wouldn't that be something?
Absolutely. And in fact, I think that's one of the, the answer is yes, and there are many good examples of that. In the climate energy system, I think this is one of actually the big weaknesses of our grand political strategy. Essentially, the world has embraced a single metric of progress, which is carbon emissions. And the problem is the real goal is to get emissions to zero, or maybe even negative. Emissions at any one point, the question is how good a metric are they for that long-term goal? And the answer is sometimes not so good. There are many things, for example, let me give you a nice example in the US. In order to really dramatically expand our use of wind and solar in the US, we would need to invest a lot in transmission. Building that transmission system in the short term provides zero carbon benefit. It doesn't reduce emissions at all. In fact, it raises them because there's a lot of emissions associated with all that infrastructure. And yet it's a critical step towards investing in the infrastructure that will ultimately lower emissions. And so understanding the relationship between short-term and long-term is often poorly done in our systems. Another example in John's domain is a carbon tax. Carbon tax by itself, a lot of economists have called for it, by itself actually helps you lower emissions a certain amount. The market gives you a theory optimized way of most efficient way of essentially achieving an emissions reduction coincident with that price of carbon. But what you really want to do is get emissions to zero. And so you need to send a long-term signal to investors for investing in technology, for investing in R&D, for all sorts of things. What you really want is a carbon price that's going to keep going up over time until the problem is solved. A static carbon price actually doesn't necessarily help you get where you need to go. It's not a bad thing. It certainly helps a little bit, but it may be the best you can do politically. We haven't even been able to do that. But it's certainly not what you need in the long run. And so this question of timescale, very, very fundamental. And I suspect in biological systems, it's the same thing, that there are indicators, but they're not often very clear. Is that you think about sort of more biomedical systems and human, well, cellular or organismic level. It's probably true in those systems as well. I mean, if you sort of say, let's think about aging, which is something you think about a lot, and you want to optimize, say, overall lifetime. What are the metrics of that in organisms' lifetime? What are the metrics of that are used to predict longevity? And how could you optimize on that? That's not typically what we do when we manage people's health, right?
Especially in a longitudinal sense.
Yes.
For the individual. Am I doing things right to improve my lifespan?
And yet, our metrics of evaluating our healthcare systems, life expectancy remains one of the core metrics, which is interesting, right? Silence.
Ginkgo?
Yeah, I have a question. I really agree with you then about what you said, the social responses to the macro changes that we're facing, probably the strongest uncertainty actually we're facing. And also, what is also kind of worry me, or at least I think we should be figuring out, is nowadays the human and social interactions is more and more mediated by different kinds of platforms, and those platforms are somewhat like has the certain mechanisms that is designed by us, and that is strongly influencing our cognition, behavior, and interactions, and then the emergent patterns out of that. So I wonder what's your knowledge about our understanding of that kind of interactions, and about the design of those kind of mediating mechanism on the platforms, and what do you think would be probably the future of the research that we should be doing about that, or understanding, or directing?
Could you just say
Yeah.
another word or two about that, about the kind of research you're talking about? Because I don't quite understand.
What I was trying to understand is that because the social responses we are going to have facing this is not just about the political leaders, what they decide, but also coming out of everyone's observation of what people or how we understand the situation, and that understanding and the human interactions, I think, is more and more mediated by the especially the digital platforms. Let's say
like Facebook,
the
Twitter, yeah.
Facebooks or Twitter, or all these kind of, because nowadays we seems to be having a stronger or longer reach of what we can know, the information we can gather, but actually it's somewhat biased according to the channels that we know that. And I think that will have a very strong influence on the kind of social responses eventually will come out of all these complex interactions.
Yeah, I've got to say,
mm.
so in the fields that I'm most familiar with, a lot of this has been done, and the approach that's been taken by people like Saul Shang at Berkeley, Michael Greenstone, an economist at Chicago, and others, has been to do a little bit what we've done in the paleoclimate community for climate science, which is to look at historical analogs. So for example, if the question is, how are people likely to migrate because of climate change? The answer is, you look at the Dust Bowl, you look at Sudan, you look at a variety of historical events, and you either do it statistically across all events, or you look at each event and analyze the movement of people. Over the last sort of 5 to 10 years, it's been in vogue for students in political science or economics to use Facebook data or Twitter data and try to say, well, how many people moved here based on this weather? Can we correlate weather in Georgia with migration in and out of Georgia? Because we have all this data now, and we can just crunch it. And that's kind of the state of the art right now. To me, this gets to what I was saying sort of with Jeffrey in mind, which is again, the value that I think SFI can provide in all of this is actually providing mechanistic theory as opposed to just patterns. Because I'm frankly not convinced that historical patterns
Yeah,
are going to result in the same types of behaviors or outcomes, because I'm not sure they just scale with the magnitude of the impacts. So, another drought of the same magnitude of the Dust Bowl, I actually don't think gives you the same exact response. And so what we need is more theory there, and I'm not sure that theory exists yet. But Walter, Jeffrey may have some ideas about this because they think about this as well. Do you want to comment?
And
I think
I'll
Jen is-
comment, yeah. There's actually, getting to your point about sort of how people make decisions, or, what their behavior is or what they belief spread. This is, a very active, growing area of inquiry, including at SFI. Like one of our resident professors who's not here right now, Mirta Golesic, looks at the influence of social networks on decision-making and behaviors and belief formation and spread of beliefs. And is working actually closely with, physicist Dan Stein and with others in order to come up with, kind of simple mechanistic models to try to understand and predict how, behaviors are adopted, how they can be changed, if at all, how they spread, and how that, influences all the things that you were talking about. So I think this is a very, and also it's informed by psychology, by, physics approaches, by, ecological network type of thinking. So I think there's it's a very active area of research. I mean, of course, it's not, there's the tendency to kind of look for the keys under the light, so you work with the data you have access to. But I think in this case, because the rise of social media and its extremely strong influence on belief formation and maintenance, I think it actually can be quite useful, but only in conjunction with kind of mechanistic theory development.
Yeah, and
testing.
because Jen, one thing you talked about yesterday was the real patchiness of data, right?
Yeah.
And it does seem to me there's a risk of the searching for the keys under the one
Yeah.
streetlight that's on. I think, for example, the kind of attribution of the Arab Spring to Twitter, that's a narrative which suits Twitter. Right. So just as the data is biased and the analysis of it is biased, I wonder if there's any. I'm just thinking of this example of the school strike, which is a growing social phenomena. I'm sure it's helped by social media, but is anyone actually looking at the kind of embodied mind of the school kids on the street and looking at how that contributes to belief formation and crowd formation?
I hope so. I don't know.
Yeah.
But it would seem like because that's an important kind of counterexample to like the spread of hate speech, which is one of the explicit projects at SFI.
Yeah.
What's the spread of, kind of positive normative behavior?
How close are we getting to theories that are good at making out-of-sample predictions? So what's the time scale of that? Is this, you talking decades or where we can really start having an impact on policy and everything? From the, again, theory to out-of-sample success that shapes things.
So I would turn to Jeffrey as an example. I think the answer is we have theories today that are directly relevant to policy.
Yeah.
Theories to explain patterns we see. Cities is a nice example. Do you want to say a few words about that, Jeffrey? Because I think it's directly relevant. But that being said, I think the cities is in some ways, there's data and therefore it was amenable to theory, but I think there are many other problems. What the time scale for developing those theories is it years to decades? Yes. Exactly when, that's hard to predict.
Sure.
But I would say it's not something that's far off into the future. I think we can point to specific examples today that are directly policy relevant tomorrow. Is that fair, Jeffrey?
Yeah, I'll talk, we have a...
Here, let's get him a microphone. Where's that microphone?
Ginkgo's got it.
Yeah, we have a session this afternoon, so I'll elaborate a little more on that. But I think the big issue, there are two issues. One is, of course, what you raised, developing the theory and so on, and understanding mechanistically how we can understand the observations we've made and put it into a framework that can make possibly some predictions with some stochasticity associated with it for various aspects. In this case, you brought up cities, of how cities function and their future and their growth and the various socioeconomic problems and challenges associated with them. So one is just developing all of that. And maybe this afternoon I'll just say a couple more words about that. But the other is the one that we've alluded to here, has been alluded to here, and that is getting a communication and a real dialogue with practitioners, with those in the trenches dealing with these problems, politicians making decisions. And that's in fact equally challenging because there is extraordinary inertia in the system. There's, urbanization and cities, just to take one example, but I think all the things we're talking about in terms of the practitioners and policymakers operate, surprisingly, in large part by rules of thumb, so-called good practice. And, from a science viewpoint, a lot of that is sort of narrative stuff that is based in ideas that, if you actually, in some cases, you can trace back to the early 19th century, and they've just sort of propagated their way through without anybody testing them, looking at them, and so on. So, but they're in the culture, so there's a huge problem. So I actually spend quite a lot of time trying to bridge that gap, and there's good faith, but very little progress. So I think that's part of the issue that, trying to, it relates obviously to the issue of, the question was discussed yesterday about acceptance of climate change and what to do about it and so on and so forth. These are highly interrelated questions.
Why don't you pass the mic to Walter? while you're-
Yeah, one thing really quickly, I think it also depends on, if you want to predict rainfall in Harvard Square, a long time. If you want to predict global average temperature, a long time ago that we had those sorts of predictions. If you want to predict the exact number of squirrels in this tree 5 years from now, hard. But if you want to understand something about sort of regional ecology, much easier. So I think it depends on what type of prediction you want.
So
Yeah,
we
but
can trash some things and then get the good coarse grain stuff going.
Yeah. So I took that for granted. I should have said that it's clear. This is a coarse grain description. It's not going to be predicting things to arbitrary accuracy, obviously, ever.
Pass to Walter. Walter wanted to jump in.
No, I just do a brief comment. Well, they don't record this. I don't know whether it's really cogent, but in the natural sciences, people have a kind of an active orientation toward data in two ways. And it's getting there in the social sciences as well. It's an interesting development. One is that one notion of active orientation towards data is that you have to generate data. And for that you need laboratory equipment. Why do you need, and that is based on complex technologies, why do you need that? You need that because nature unassisted doesn't provide you with the high energies, for example, that are needed to observe not yet to find not yet observed effects. So that's why you need superconducting supercolliders. So the notion of an experiment, is central and productive in the natural sciences. It's more difficult in the social realm.
Less so in the social sciences.
And secondly, the other active orientation towards data is in some sense precisely theory. And theory has one aspect of theory to me seems to be one job of theory is in some sense to deny the data, because theory should come up with constructs, quarks, colors, and what have you, black holes, that might at some point in time require you to reorganize the data that you already know and reinterpret them. So that's another notion of active orientation towards data that is characteristic for the sciences, and I wonder, whether to what extent that is ever achievable in the realms that you're concerned with.
Jeffrey?
Can I just elaborate briefly on that? I think I want to just change slightly what you said about the role of theory, because I think a critical role of theory in all science, and it becomes maybe even more important in the historical sciences, where you can't do what you said, that is have laboratories and do experiments, and the operative thing is controlled experiments, that you can control the variables. But one critical aspect is, even if the theory is incomplete and even if the theory is wrong, it provides questions, and it provides questions often that don't normally occur if you are just simply sitting as a qualitative observer. And as a corollary to that, it also provides a framework for saying, my God, these are the kinds of data we should be concentrating on. These are the important data, maybe, rather than having the image that is developing in the era of big data, that it's somehow democratic and egalitarian. In fact, that's one of the things that those that propose it use as an argument, that all data is equal, which I think for any serious scientist is clearly bullshit. Quite the contrary. I think we're highly prejudiced, and our theories tell us how to be prejudiced and give us a rational basis for that. And I think that's crucial.
I would say as a geologist, we're a little bit different, Walter. For the most part, it's not that we don't do any experiments. We can, take rocks and minerals and, squeeze them and heat them, and we can do all sorts of thermodynamic experiments, kinetic experiments. But the fact is, when you're dealing with timescales of millennia to millions of years to billions of years, and you're dealing with many processes that are far too slow for a typical PhD timescale, even something simple, the kinetics of calcite dissolution on the deep sea floor, which takes thousands of years, is still a little long for an undergraduate thesis. You could maybe assign a PhD student to it, but it would be problematic. And so we're used to dealing with reading the experiments that have already been done and being clever with finding where in the natural world that particular experiment has been done. But of course, it's never done in exactly the way you would do it in the laboratory, and so you have to, one of the state of the art is to understand its differences and understand what you can learn from it and what you can't learn from it. But what you said is exactly right, which is ultimately you make predictions that then can be tested by going and making additional observations. In your case, with additional experiments. In my case, by saying, okay, this makes a prediction about if I go look for this particular thing in the Earth system, this is what I should find, and I can test it that way.
That is important to specify some kind of evidence.
Absolutely. Absolutely. I think John has a question. Get him the microphone.
I just want to tell three quick aphorisms. Okay, three quick aphorisms about the role of theory. The Coles Foundation, which pretty much is responsible for creating mathematics and economics, or emphasizing mathematics and making it established in economics, its motto was "No measurement without theory." On the issue that Dan brought up, I said this yesterday, but I think it's worth repeating about it's the reaction to the changing climate that's going to be possibly even more interesting than the climate change itself.
I agree.
It's a chess aphorism that it's the second mistake that kills you. And then on the business about predicting, the rainfall in a neighborhood, and I'm going to repeat a story that my thesis advisor told, and probably told some of you here too. He was, Ken Arrow, was in World War II, worked in the U.S. Weather Bureau, and Eisenhower asked them personally to choose the day of the D-Day assault 3 months in advance. So they wrote him a letter, and they said they couldn't possibly figure out which day it wasn't going to rain. It was just beyond the powers of meteorology at that time. And Eisenhower wrote back, and he said he understood the limitations, but it was still very important to the war effort. So,
Well, we will break for 10 minutes, and then we will reconvene for our next panel
Thank you.
on intelligence.
And could I just ask people one favor? So this is a quiet time because it is the lull before the storm. Undergraduates have mostly gone away. Commencement is next week, and so this is a quiet week on the Harvard campus. But and so the Center for the Environment here is delighted to have SFI here. I feel like it's family and it's wonderful. But there are some staff who've been really working hard to support this effort. Jim Clem, Aaron Harleman, Jill out there. So if you have a chance to just pat them on the back and thank them for their efforts, it would make my life a lot easier. So I appreciate it. Thank you.
And in the vein of thanking people, let's thank all the panelists and the moderator.